Yes.
Okay, nice. I'll get started. So, uh, a second. Okay. Hello, I'm Yihong. Today I want to talk about our work on relational imaging. And in this talk, I want to show how relational imaging is simpler, faster, and optimal. So let's get started. Our main contribution is relational imaging, which views the imaging problem from a relational perspective. In particular, we transform an Egraph to a relational database and an imaging pattern to a conditional query. And a conditional query is a subset of relational queries that only involves relational joins. So by doing so, we can utilize the decades of research that is done in the database community to improve imaging. So let's see what this entails. Egraphs are everywhere. It is a data structure that has wide applications in both program optimizations and theory solving. It is used by many recent projects, and there are many success stories about using egraphs. Generally speaking, there are two applications of egraphs. One is program optimization. The technique is known as equality separation, and it keeps many equivalent programs in a single egraph and performs non-destructive rewriting until a fixed point is reached or a timeout happens. On the other side, on the other hand, the egraphs are also used for assembly solving. It is used to solve the theory of equality with uninterpretable functions and used to combine different theories in assembly solver, which is a process known as Nelson-Alpen procedure. Okay, so what is an egraph? An egraph represents a set of terms and a congruence relation efficiently. It consists of e-classes and e-nodes. So e-classes are just a set of e-nodes, and e-nodes are operators that connect to children e-classes. So an e-graph can represent many terms. For example, the e-class CF represents F1G1, as you can see from the e-graph on the right, and it can also represent other terms such as F1G2, F2G1, and so on. And all the terms that are represented by same e-class are equivalent to each other. So for this example, this e-graph represents of n square many terms, but in general, an e-graph can represent exponentially many terms. So this is one of the reasons why e-graph got so powerful, and as we'll see later, this is also why imaging is an NP-complete problem. Okay, so imaging is basically pattern matching over an e-graph. More formally, we can define imaging as finding substitutions from variables to e-classes, such that the substituted terms are represented by the e-graph. So taking the e-graph result before, for example, the pattern f alpha g alpha will match f1g1, f2g2 to fngn, and all of them are witnessed by some substitutions. For example, f1g1 is witnessed by the substitution mapping alpha to 1 to the e-class 1, because if you instantiate the pattern by substituting alpha with e-class 1, the expression f1g1 is contained in this instantiated pattern. Note that a substitution can witness multiple expressions at the same time. So for example, the pattern f1 alpha will match f1g1, f1g2 to f1gn, and all of them are witnessed by a single substitution, which maps alpha to CG. Okay, so imaging is an NP-complete problem, and this is why many existing imaging algorithms use one form of backtracking or another. And the NP completeness is with regard to the pattern size. So this is what we call the query complexity. And also, imaging is responsible for a majority of the runtime in practice for applications like equality separation. So it is fair to say that imaging is a bottleneck in scaling up egraph-based applications. Okay, so let's take a look at the existing imaging algorithms. Taking the pattern f alpha g alpha, for example, they'll first try to go over all the e-classes in the e-graph, and for each such e-class, go over all the f nodes in this e-class and build the corresponding substitution. And then it goes over all the g node in the second child of the f node and check if the mapping for alpha in the two occurrence is equivalent. If yes, it yields it, otherwise it continues search. So you can see there's two major loops here, and each of them can take as long as of n many times. So in total, this algorithm runs in of n squared time. Yet, if you look at the pattern, you will find that this pattern will admit at most of n many matches. So you can see there's a discrepancy between the maximum number of matches and the actual performance. Okay, so in summary, existing imaging algorithms relies on naive backtracking. The literature has proposed several ad hoc optimizations for specific patterns, but most of them focus only on constant time speed up, and there's no principal way of performing such optimizations for all patterns. And there's also no data complexity bound in the literature. So as we saw before, imaging is an NP-complete problem, but this is with respect to the query size, which we call query complexity. But in practice, we are more interested in the data complexity, which is concerning the performance of our query with regard to the size of the egraphs. However, there's little literature on data complexity of the imaging problem. Okay, so our work is based on the observation that imaging and conditional queries are structurally similar problems because both can be defined as finding substitutions such that the substituted terms or items are present in some database, whether it's an Egraph database or a relational database. Based on this observation, we have the following workflow. We first take a list of patterns and an egraph, and then we transform the egraph to a relational database. And then we transform the list of patterns to a list of conditional queries. Note that here we are taking a list of patterns, and this is well suited for applications like equality separation to amortize the cost of building the. So we are taking a list of patterns because we want to amortize the cost of building the relational table, and this is well suited for applications like equality separation because in such applications, egraph imaging are always performed in batches. So let's see how an egraph is a relational database. Basically, we build relations for each functional symbol. So in this case, they are f, g, and the number 1 through n. So taking the binary function f, for example, we have 3 columns. The first column is the e-class ID of the corresponding e-node. And the rest of the 2 columns are the children e-classes of this corresponding e-node. And so taking the tuple cf, 1, cg, for example, this tuple present in such database because the corresponding e-node belongs to the e-class cf and has children e-classes 1 and cg. Also note that here we are treating constant symbols as functions with zero arity. So that's why a relation R0, R1 to Rn are all just single column, which denotes the e-class ID where the corresponding e-node resides. Okay, so this schema allows us to transform the pattern to a conditional query by simply flattening the pattern. So taking the f alpha, g alpha, for example, we simply unnesting each sub-expressions and introduce actual variables to join the relation together. So here we are introducing the extra variable x to join the relation representing f and the relation representing g. And this is all we need to do. And if you look at this pattern, you'll find that it has a very efficient plan using hash joins. So you build indices on Rg, and then you scan over Rf to check if there's any matches. So as you can see, there's two loops that takes linear time. So the overall runtime is linear, and so we reduce the time complexity from O of n squared to O of n, which is asymptotic speed up. Okay, so why is our approach faster? If you look at the original imaging algorithm, you'll find that it tries to enumerate all the terms that have the same shape as the pattern, but not necessarily have the same mapping for all the variables. And it only checks for the consistency of the variable mapping before yielding. Well, in our approach, we start by building indices on both alpha and x, and we only enumerate terms where constraints on both are satisfied. And here we are calling the variable x the structural constraint because it denotes the kind of the shape our matched expression should look like, and we are calling alpha the equality constraint because it denotes that for all the occurrence of alpha, the mapping should be the same, should be equivalent. And the traditional imaging can only explore the structural constraint during query planning, and they handle equality constraint suboptimally. So that's why we are able to synthesize asymptotically better plans. Okay, so here's a comparison between our approach and the traditional imaging. As we just saw before, the traditional imaging only exploits structural constraint, while our approach explores both, allowing asymptotic speed up. Moreover, the traditional imaging only performs a top-down backtracking search, while in our approach, we can perform the search in whatever direction, allowing the query automator to find better plans. So here's an example. Consider the pattern f of g of h of x. If you image this pattern on an E-graph with only one h node, the traditional imaging will perform a top-down backtracking search. So you will go over all the f node and then all the g node, which will take, in worst case, of n squared time. While in our approach, if our query automator is able to find that there's only one tuple in the relation representing h, then it will start the search, start the join at this point, and once it fixes the h of x, the whole pattern, the whole term will be determined immediately. So we reduce the time complexity from O1 squared to O1. And finally, as we talked before, there's little theoretical guarantees of the traditional imaging approach. While in our relational imaging approach, we achieve optimality by adapting results from the database research. So in particular, we proved two data complexity results. As we talked before, the literature has mostly focused on the query complexity, but it is usually more useful to consider the data complexity, because in practice, the imaging pattern is usually small and of constant size, while the E-graph keeps growing. So we are more interested in how the imaging will perform with respect to the growing E-graphs. So this is the first theorem. It concerns the worst-case optimality of our approach. In particular, we are considering all the E-graphs with the same size. So here, if you give me an E-graph with size n, the runtime complexity of our approach will be the maximum output size an E-graph with size n could ever achieve. So the proof of this theorem is just a direct application of database research on worst-case optimal join algorithm, because our relational imaging uses WCOJ as our subroutine for solving the generated content queries. The second theorem is more involved because it uses the structure of the compiled content query in the proof. Here we are considering all egraph instances, so we are considering each specific egraphs. And here we are bounding the runtime as a function of the egraph size and the actual output size. So we did some evaluations. We use the two largest test suite of Egg, which is a state-of-the-art egraph framework, and our baseline is X imaging procedure. We use generic Zhang algorithm, which is one kind of worst-case optimal algorithm solving the content queries. And we also run twice, once with index building and once without. This is because we need to build indices to perform the actual join in our approach. So we would like to see how building indices will affect the performance of our approach. So here is the result on one of the benchmarks. We saw the patterns by the size of the output. So on the left are the patterns with the most output size. The y-axis denotes the times of the speed up we achieve compared to the baseline. So larger is better. And the blue bar denotes the time with without index building, and the orange bar denotes the time with index building. So you'll find that for some patterns, the time to build indices takes a lot of time. So this somehow mitigates the benefits of our approach. And we see that for most patterns, we achieve good speed up. Also, so on these specific patterns, we achieve more than 6 orders of magnitude speed up. This is because this pattern is more complicated, and so that's why we achieve a good speed up. So in general, the more complicated your pattern is, the more we can achieve, the more significant the speed up we can achieve. Moreover, on these linear patterns, we achieve a similar performance. This is because we don't have extra equality constraint that we can use. So we have no additional information than the traditional imaging. So that's why we have the similar performance. However, what is more interesting here is that we do achieve a great speed up on specific linear patterns. So the pattern here is a plus minus 1 times b. And our query optimizer is able to achieve such speed up because it noticed that there's only one such constant as minus 1. So if it starts the search from this direction, then the search space will be much smaller. So this will be potentially harder to do in the traditional imaging approach. And finally, to show how our approach is widely applicable, we show we can support multi-patterns naturally. So multi-pattern is an extension to imaging where a list of patterns need to be matched simultaneously. This problem is studied in the literature, and there are many practical applications of it from both the theory solving side and the program optimization side. While this may be difficult or suboptimal to do in the traditional approach, our relational imaging supports them for free because we just nesting each pattern and concatenate the resulting continual queries together. Not only it's simple, it's also get all the benefits of relational imaging for free. So, for example, it can you can get the say efficiency, you can get the optimality for free. And finally, there's some future work that I'm really excited about. So one of them is incremental imaging. So this is a problem that has been also studied in the literature, and this is a hard problem. But we found that it may be possible that this may be just a reinvention of a classical problem in the database community, which is incremental view maintenance. So we hope that if we can utilize the research done on the incremental view maintenance, we can further improve incremental imaging. And currently, our projects of our relational imaging only implements a very tiny implementation of generic join. And the query optimizer is also very simple. So we would like to explore more design space of the join algorithms and their optimizations, because the database community, again, has proposed a lot of such algorithms. So we would like to try these. And finally, our projects hints on the possibility of building next generation Egraph framework purely on top of DBMS. And in fact, we have built a prototype with SQLite that supports all the standard operations of egraphs and express them all purely on top of SQL queries. So this is very cool because we can get all the good properties of DBMS for free. So you can get persistency, scalability, concurrency. So you can imagine we can build that future egraph framework that is scalable, distributed, transactional, and so on. So with that, this concludes my talk, and I would like to take any questions.
Great. Thanks, Yihong. We have plenty of time for questions. Luckily, I'll take some from the in-person audience.
Hi, Thomas Wies. Thank you for the nice work. I have a question. Did you compare against imaging code trees like they're implemented in Z3? I mean, they're designed to do many queries sort of simultaneously, right, for different patterns, a bit like an OR query. Would you support something like this?
Right. So I've saw this paper before, and this is where like our work get inspiration. So I think the code tree is somehow complicated, and I think this will also use this to support incremental imaging. And this is something we currently didn't do, and we would like to try. And also we have like different scenarios. Like I suppose that in SMS solvers, there's multiple queries to be run simultaneously. While in the workload of equalization, where we are currently focusing on, you only have like say a dozen of patterns. So and also if you do the code tree, I suppose that it's not very compatible with the relational approach. So it's also interesting to see if how they can integrate with each other.
Very nice work. Really cool connection between with relational database stuff. My question is about, so you generate conjunctive queries. Have you thought about what happens if you if you generalize to full data log programs, or maybe with negation, if you end up with something that solves a much more general problem than egraphs?
Oh yeah, this is cool. So this is our ongoing work. We try to express egraphs as data log and try to get all these good properties of data log, like incrementality and semi-naive evaluation. But yeah, we do meet some difficulties because it's hard to express egraphs just in pure data log. We need some extensions, and this may be tricky in general.
Okay, let's take a few questions from the online audience. The question is, can I extract the equality proof that the substitution is equal to the match? If not, what are the challenges?
I'm not sure I understand the question. So is it saying that the substitution from the imaging is... sorry, could you elaborate on that a little bit?
This might be hard to do the online audience, but I guess what Ho had meant was that maybe you can extract a proof term, or maybe explicitly what the substitution is from the query, and then use that programmatically somewhere else. Maybe Ohad can comment on.
I see. So I think the match is already kind of a proof or witness of the imaging, because once you get the match, you can just use it to find whether it's present in the egraph or not. I'm not sure if I understood the question, but we can also discuss offline.
So here's another online question. Is the correspondence between E-matching and conjunctive queries one-to-one?
So on the surface level, it's one-to-one. So you can map each imaging pattern to a kind of query. But the thing that is not one-to-one is the egraphs and the database, because on the egraphs there's the functional dependency, while a pure database do not have such. So it's okay to map an egraph to a database, but not the reverse way. So you can map a database or like an arbitrary database back to egraph. There's some functional dependencies that need to be satisfied.
Okay, we have time for a few more questions. I'm going to take a few more from the in-person audience. I think Favonia had a question.
Hi, so I'm Favonia from University of Minnesota, and very nice work, thank you. So I have a technical question. So when you're using the join algorithm, do you have to generate the actual table first before applying the join, or can you just avoid that step?
So currently we create a table for each imaging will be performed. This is because the egraph is a tree structure, and it's quite hard to just directly perform the kind of queries on that. So that's also why this traditional imaging approach performs a top-down search. So in our approach, we first flatten the egraphs to perform the actual kind of query. So this is also like one of the I guess lower point of the approach.
For maybe a couple more questions. Let's take another one from the online audience. Do you think your technique can be used to improve E-matching in SMT solvers?
Yeah, I think that's a good question. I think my current answer is I don't know. So our current focus is on the workload of equality separation, and I suppose that for SMT solvers they have a quite different workload. So I'm not sure if they can be applied to SMT solver, but I think it's kind of a future work, and I think maybe SMT solvers can be inspired by this work.
All right, let's take one last question, I guess. Can you explain where the speed up in benchmarks without nonlinear patterns comes from?
Right. So Yes. Could you switch to the slide? Right here. So for this nonlinear pattern, so we define nonlinear patterns as the pattern where the variable, there are multiple occurrence of the same variable. So this is where they generate the equality constraint. And for this equality constraint, basically the traditional imaging handle them suboptimally. So they basically don't consider them and only check for them before yielding. So in our approach, we take them into consideration and put them at the same importance as the struggle constraint, and they are take into consideration at the same time to require planning. So we generate more efficient plans.
All right, I think we can stop here. Let's thank our speaker again.